Hi, welcome to video on control systems concepts on compensations. So in this video we'll see design of a lead compensator using Bode plots. So we'll start with one of the design problem, which is having a compensator in the form of DFS block, and there's a plant having a transfer function 1 over s into s plus 1. There are three parts in this particular problem. So one is to, by considering this DFS as k, we are supposed to find that value of k which corresponds to a velocity error constant of 12. And with the value of k that we found for part A, let us find out what is the phase margin of this system. And then in the third part we are asked to design a compensator which can give a phase margin of more than 30 degrees. So to start with, let us assume this DFS as k and then try to find out what is the value of k, so that kV is 12. We know this expression for the velocity error constant, which is given by limit of s and 0 s into the open loop transfer function, which is supposed to be 12. So now you can find the value of k from this, which is coming out to be 12. So first part of the problem in which we have to have a value of kV as 12. So for a value of kV is equal to 12, we are supposed to find the value of k, the constant of this DFS. Now it is 12. So with this DFS as 12, we will actually find out what is the phase margin of this particular system. So the transfer function comes out to be 12 into s into 1 plus s. So omega GC is coming out to be 3.39 by equating this magnitude to 1. And this is a phase equation, and omega GC, that is phi of omega GC, the phase at which the phase corresponding to omega GC is actually minus 163.6, from which we are going to get the phase margin as hardly 16 degrees. Actually the gain margin is infinity. So let us verify this phase margin, gain margin using 20 sim quickly, and then we'll go to part C of this design. Let us see the pole positions here. As you can see, the poles are at 0 and minus 1. You can see the same pole is at 0 and minus 1. The system gain is 12. So that's what is system gain is 12. So here we end up with omega GC as 3.39, which you can see here. This is frequency corresponding to gain cross of frequency, which is magnitude 1. You can see now it is 3.39 radian per second. That's what is this 3.39. And the corresponding phase margin is 16 degree. You can see this is 16.41 degrees. So this is what is 16.4 degrees what we have theoretically. This is using 20 sim. So this way we can able to verify one-to-one the theoretical values and the simulated values. So let us move on to part C of this design. Okay, part C of the design is involved with introducing this DFS, which is a phase lead network. So and we should get the phase margin of 40 degree. So actually after compensation, the phase margin is 40 degree. So we know that whatever existing phase margin is hardly 16 degrees. So we are supposed to add another 24 degrees from this DFS. But this 24 degrees is not enough, because whenever we actually introduce any network, the omega GC, the gain cos of it, will shift to right side, which will further reduce the phase margin. Now to account for that shift in omega GC, we are adding another 5 degree onto that, whatever that is required to be added by this DFS. So we will now consider 24 plus 5 degree, which is 29 degree. Approximately 30 degree should be provided by this DFS, so that the overall system should give a phase margin of 40 degree. So that's why we have it as 30 degree. So in the design of this particular phase lead network, we have an expression for the transfer function of this phase lead network is given by 1 plus ts by 1 plus alpha ts, where alpha is obtained from the required value of maximum phase shift. So since the amount of maximum phase shift required is plus 30 degree, from which you can get the value of alpha using this equation, that is 1 minus sin phi m by 1 plus sin phi m, which comes out to be, for this particular case, it is 0.33. So with this value of alpha 0.33, we will actually find out what will be, of course, since we are having this DFS as k is not consider this k for the time being. Let us consider only this 0 and pole terms. When you're considering only this 0 and pole term, this k, then this happens to be 0 dB, and since it is plus 20 per decade, so this is 0 dB and it is keep increasing with a slope of plus 20 dB per decade. So with this at 0 dB magnitude, we can actually find out what will be the amount of magnitude that may come when the frequency corresponds to maximum phase shift we have. So that can be obtained using this expression. So in the value of omega, you substitute the value corresponding to the theoretical value corresponding to omega c. That is, omega c is actually the frequency at which maximum phase shift occurs, so which is given by 1 over root alpha into t. So upon substituting that value of omega as this, and then we will end up with the magnitude of this particular plot will be 1 over root alpha. So in this particular example, since we already know the value of alpha as 0.33, so 1 over root alpha comes out to be 1.74, which corresponds to 4.8 dB. So if this is 0, and at this particular frequency this will be 4.8 dB. That's what is the meaning of this particular thing. So since this phase lead network is adding a magnitude of plus 4.8 dB, we have to ensure that so our omega GC should be at a point where this 4.8 dB has to be nullified by this transfer function, the original transfer function GFS. Now you try to identify that frequency which corresponds to a magnitude of minus 4.8 dB of GFS. Meaning, so we have this as the GFS magnitude equation, 12 by omega into under root of 1 plus omega square. So you are looking at minus 4.8 dB, which is in ratio comes out to be 0.575. So you find out at what value of omega you will get this as 0.575. So at this frequency we have a magnitude of minus 4.8 by this GFS. Now this GFS cascaded by DFS, so at minus 4.8 plus 4.8 at this particular frequency, we will actually have a zero crossover frequency. So this is the frequency corresponding to new zero crossover frequency, because you might have seen in the previous slide that without this DFS, that is without the poles and zeros, we had omega GC as 3.39. When you have these poles and zeros here, this will actually shift to 4.51. So that's what is the meaning of this here. So this will actually shift to 4.51. This is a new gain crossover frequency of cascaded DFS into GFS. So using this new gain crossover frequency, we can actually find out what is the zero and pole position of the phase lead network, which happens to be 2.6 radian per second and 7.81 radian per second. And this is the time constant representation. This is the pole zero representation of DFS. We can actually find out what is the overall transfer function of the cascaded system, that is DFS into GFS. So this is the overall transfer function of the system. Now it is 12 into this is the zero position, and you have 3 poles here. The poles are there at 0, minus 1, minus 7.81, and there is a 0 at minus 2.6. Now this is the pole positions. As you can see, we have 3 poles and a 0. This is that 3 poles and a 0 here. The system gain is 12. So this 36 is actually the root locus gain, and you can actually find out whether the value of kV is 12 for this compensated network or not. So now you have DFS to GFS, which is exactly the pole zeros and the original pole zero of the system. You can see now you are getting this as 12. So we can actually find out what is the phase margin, and of course the gain crossover frequency and the phase margin. You can see after compensation, you had a phase margin of 16 degrees before compensation, before having this DFS in the, along with poles and zeros. You can see this omega by adding this compensation network, so the phase margin has increased from 16 degree to 42.5 degrees. But what we started with is we are supposed to have a phase margin of more than 40 degrees. That is now achieved. along with the desired value of kV, which is 12, which is also coming now. So let us go to 20 sim and then try to find out whether the phase margin of this compensated network with this transfer function is at 42.5 degree or not. This is actually the theoretical calculation. So let us go to simulation, then redo the same thing. Okay, let us see this compensated entire transfer function. You can see now the system gain is 12 here. You can see the system gain is 12, and you can see the poles are at 0, minus 1, minus 7.81. You can see poles are 0, minus 1, minus 7.81. You can see there is a 0 at minus 2.6. You can see 0 is at minus 2.6. That can be edited over here. You can see this is minus 1, 0, minus 7.8, and you can see 0 is at minus 2.6. So upon doing this, you can see this is your border plot. So border plot is showing a phase margin of 42.53 degrees, which is evident here also. Here also you can see it is 42.5 degrees. You can see omega GC is 4.5 radian per second. If you can see here, this is the frequency corresponding to gain crossover frequency where the magnitude is 1. So this corresponds to 4.5 radian per second. So this way we can able to get the desired phase margin of 40 degree by using a DFS. Of course, let us also see whether this, okay, what is this, how do we get this 4.8 dB? So this 4.8 dB what we are talking about. So let us edit only the transfer function of the compensation network without having that K term. So let us make it as only this 0 and poles, and then see at 4.51 radian per second are we getting that 4.5 dB or not. That is this is plus 4.8 dB. So this should be plus 4.8 dB. So let us go to this transfer function. Then let me delete this particular. Let me delete this as well as this. Let me have the system gain as only 1. So because we don't have the system gain as 1, so we don't have any system gain here. You can see this is only this poles and zeros. Since we this is before actually knowing the poles and pole and zero portion, it was found out to be 4.8 dB. That's what is 4.8 dB. Let us verify even after knowing the values of poles and zero portion, is it coming out to be 4.8 dB or not. We can actually predict this before actually knowing the values of 0 and pole position, because we know this expression of omega value, omega which corresponds to maximum phase shift theoretically as 1 over root alpha into t. So let me just go to this and then try to find out so whether this is coming out to be. So let us find out what is the maximum value. So let me just find it here. You can see now the maximum value. I am just looking for the phase shift at which where it is maximum. You can see phase shift is maximum here, which is 30 degree. So that's what we wanted. This network should introduce 30 degree. So this is 30 degree to be introduced. So that is what is being introduced by this particular thing. Let me again find out what is maximum. You can see it is 30 degree and the corresponding frequency is 4.5. So let us go to this magnitude plot and see at 4.5 radian per second whether this is 4.8 dB or not. So of course it's not 4.8 dB now because it is in terms of magnitude. So it will be 1.74. So let me just look for this at 4.5. At 4.5 I should get 1.74. So let me just see here. Okay, this is somewhere here. You can see this is 4.5, so I'm getting it as 1.74. This is what we are looking at. This is the at this maximum at this particular frequency which corresponds to maximum phase shift. The magnitude of this phase lead network is 4.8 dB or 1.74. It is 1.74 in terms of ratio, which is 4.8 dB. So since it is introducing 4.8 dB, we are identifying the corresponding minus 4.8 in this GFS and the corresponding omega. The corresponding omega is 4.51, which exactly corresponds to this particular frequency at which we exam. No need to actually verify this. This will be exactly at 4.51. So since we are nullifying that 4.5 with this minus 4.8, So the crossover frequency is also 4.5.